Have you ever stopped to think about how an airline juggles thousands of flights a day? Or how a delivery service gets millions of packages to your doorstep like clockwork? Well, the secret isn't just good planning. It's a powerful mathematical tool working silently in the background, a hidden engine that basically makes our modern world run. Today, we're pulling back the curtain on that engine, linear programming. Now, to really get why this is such a big deal, you have to appreciate the sheer scale of the problems it was designed to solve. We're not talking about your high school algebra homework. We are talking about logistical nightmares, puzzles so vast, so tangled, that for decades they were basically unsolvable. And this wasn't just some theory. For the US Air Force, this was a very real, very massive headache. Can you even imagine trying to make one single perfect decision when you have to juggle 150,000 different factors all at the same time? I mean, where would you even begin? That was the challenge they were up against. So what was their problem? Oh, it was the mother of all logistics puzzles. They had to schedule thousands of planes, pilots, and crews across countless routes all over the world, while also hauling cargo and people. Every single piece of that puzzle affected every other piece. You change one flight time in Germany, and suddenly you've got a ripple effect that could disrupt the entire system in Japan. Getting it right meant saving millions. Getting it wrong? Total chaos. And this is where linear programming, or LP, as we'll call it, makes its grand entrance. You gotta understand, it's so much more than just math. It's a whole framework for making the best possible decision when you're boxed in by a ton of different rules and limits. Think of it as the art of finding the highest peak of a mountain when the terrain is unbelievably complex. Okay, so what is it exactly? At its heart, linear programming is a way to get the best result, say the most profit or the lowest cost, from within a set of rules or constraints. Now, the key word here is linear. Everything, your goal and all your limits, has to be describable with straight lines. No curves allowed. It's about figuring out how to win the game while playing strictly by the rules. To really wrap your head around this, it really helps to see it. So let's take one of those massive problems and shrink it way down to just two variables, something we can actually draw on a piece of paper. So how does LP visually hunt down that perfect answer? Well, the process is actually pretty straightforward. It breaks down into four main steps. First, you have to clearly define your goal and all of your limitations. What do you want and what's stopping you? Next, you actually plot those limits as lines on a graph. Then, you find the special area where all your possible solutions can live. And the last step? You just check the corners of that area to find the single best one. Here's how it starts to take shape. Every single rule, like you only have 100 pounds of steel, or this machine can only run for 40 hours a week, becomes a simple straight line on our graph. These lines are like fences, literally drawing the boundaries of what's possible. So, when you draw all these lines, something really cool happens. They fence off a specific shape. This shaded area where all the rules overlap is called the feasible region. Any point inside this shape is a valid, possible answer to your problem. But here's the thing, we don't want just any answer. We want the best one. And this brings us to the absolute magic trick of linear programming. The single best answer, the perfect solution we're looking for, isn't hiding somewhere in the middle of that region. A fundamental theorem proves it will always be found at one of the corners, the extreme points of that shape. And that, right there, dramatically narrows down our search. Okay, so checking a few corners on a simple 2D graph, easy peasy. But what happens when we jump back to that Air Force problem with its hundreds of thousands of variables? You can't exactly draw that on a whiteboard. You need a much, much more powerful way to handle that kind of complexity. I mean, that's the real kicker, isn't it? How on earth do you find the corners of a shape that exists in thousands of dimensions? For a long, long time, the methods they had were smart, sure, but they were also frustratingly slow for problems this big. To help visualize this, let's use an analogy. I want you to imagine that feasible region, that shape of all the possible solutions, is no longer a flat polygon. Instead, picture it as a massive, multi-dimensional geodesic dome, like a giant, complex crystal with countless flat faces and sharp corners. The best answer is sitting at one of those vertices. The question is, how do you find it? And this analogy perfectly sets up the two main ways to solve it. For decades, the go-to was the simplex method. Think of it like an ant, carefully crawling along the edges of that giant dome. It moves from one corner to the next, checking the value at each stop. until it's sure it has found the best one. Then, in 1984, a brilliant mathematician at Bell Labs named Narendra Karmakar announced a true breakthrough. His method didn't bother with the edges. It took an incredible shortcut, tunneling right through the inside of the dome to get to the answer way, way faster. And the difference in speed was just staggering. We're not talking a little bit faster. For these huge, complex problems, Karmakar's method could be over 50 times faster. This was the innovation, the complete game changer, that finally gave organizations like the Air Force the power to solve their hideously complicated problems and find efficiencies they never thought possible. So why does all this math history matter to you? Because that breakthrough unlocked the power of optimization for, well, pretty much everyone. Today, linear programming is that invisible engine running countless systems that we all rely on every single day, whether we realize it or not. You see it everywhere in transportation. It's figuring out the most efficient flight and crew schedules for airlines. It's plotting the fastest routes for delivery trucks. It's even working out the best way to move bikes around a city's bike share program, so there's always one waiting for you when you need it. Its impact is just as huge in the world of business. It helps factories plan their production schedules to make the most of their resources. It's behind the scenes of online advertising, deciding which ad to show you to maximize the chance of a click. It even helps banks structure loan offers to perfectly balance their potential profit against their risk. And get this, it even has life-saving applications. It's used in healthcare to optimize hospital supply chains, making sure they have what they need when they need it. And incredibly, it's used to organize these complex kidney donation chains to find the absolute maximum number of compatible matches. It's literally saving lives. But wait, there's more. Linear programming has one last secret to reveal. And honestly, it might be its most powerful insight of all. It can tell you the hidden value of the very things that limit you. It's a concept called the shadow price. Just think about it for a second. In any project, you have limits, right? Not enough time, not enough money, not enough materials. But are all those limits equally important? What if you could get just one more hour of someone's time, or one more pound of a key material? What would that actually be worth to your final goal? Well, L-Key can tell you. Exactly. The shadow price is the precise amount your profit would go up or your costs would go down if you had just one more unit of a scarce resource. It's the hidden economic value of a constraint. In other words, it tells you exactly how much you should be willing to pay to get a little bit more of something you've run out of. This simple example from a furniture factory makes it all click. Look at machine 2, the sander. It isn't being fully used, so its shadow price is 0. Getting an extra hour on that machine is worthless. It's not the bottleneck holding up production. But machine 1, for assembly, is maxed out. It is the bottleneck. And its shadow price tells us that one extra hour of time on that specific machine is worth exactly $5 to the bottom line. It pinpoints what's really holding you back. And that really is the ultimate power of this incredible tool. It doesn't just give you the best answer, it reveals the hidden economic landscape of your entire problem. It shows you the true value of your limits. So that leaves us with one final question to think about. What's the key constraint, the main bottleneck, in your work or even in your life? And what is its shadow price? What would it truly be worth to you to solve it?